I will share my screen. I think there we go. Okay. Hopefully you can see everything and you can hear me all right.
We can hear you.
Perfect. Okay. So first off, thanks everyone for being here and for this opportunity to present this. This is very new research. We barely just have sort of our working draft that we will post hopefully soon. But this is continuation of work we've been doing, and this is joint work with Buzz Brock, Lars Peter Hansen, and Hong Zhang at Wisconsin, Chicago, and Argonne National Laboratory. So this is building on some of the recent work we've done where we've been exploring the impact of uncertainty, and here we're looking at how climate change uncertainty should impact social valuation and policy. What's important about that is that as we've dug into this, we've realized that there's some really interesting policy channels and mechanisms that keep coming up and that we've wanted to explore and understand. And today will be sort of a realization of some of these interesting policy implications that we've been wanting to explore. So let me start off with a couple of quotes. The first one comes from two of the most recent IPCC working group reports. And it introduces a very sort of interesting tension that we think is critical in this analysis. It says, it's unequivocal that human influence has warmed the atmosphere, ocean, and land, and human-induced climate change, including more frequent and intense extreme events, has caused widespread adverse impacts and related losses and damages to nature and people beyond natural climate variability. And yet, at the same time, in a recent paper from James Rising and co-authors, it says the economic consequences of many of the complex risks associated with climate change cannot, however, currently be quantified. These unquantified, poorly understood, and awfully deeply uncertain risks can and should be included in economic evaluations and decision-making processes. So, and this is sort of at the heart of what we're interested in, understanding that there are sort of clear and obvious implications related to climate change that need to be taken into account, and yet not being fully able to quantify and understand how severe these consequences may actually be. And so our question of interest is really thinking about the socially optimal policy response to climate change. What makes this obviously challenging is that there are multiple externalities or negative adverse outcomes that need to be addressed at a societal, national, international level. Things about climate change, economic risks, about innovation. There's various climate policy levers to consider, whether it's abatement of carbon emissions or again, innovation, technological change. And there's different sources of uncertainty to consider, both on the geoscientific and economic side. And we want to address this in a general equilibrium framework that applies decision theory to evaluate the impact of uncertainty on climate policy outcomes. So what we're going to do specifically in this paper is account for the consequences of multiple uncertainty sources. The first would be the carbon climate dynamics, this mapping of emissions into temperature. Then there's the economic damage functions, which depict climate-linked output losses. And we also want to think about technological innovation and these shifts that would reduce carbon abatement costs and help us move towards a carbon neutral economy. And we're interested, when I say uncertainty, in thinking about multiple types of uncertainty. This includes risk, which would be within models, these explicit random impulses where we know distributions, but we just don't know the realization. You could think about this as ambiguity across models, where you have multiple model parameterizations and you're not sure which one's correct, as well as misspecification about models, where we have these incomplete abstractions that our models try to represent what's going on, and they may be potentially misspecified or incorrect. We want to embrace all of these rather than putting them to the side and confront them directly in a unified framework. And I'm going to try and present to you at a high level this framework, and hopefully that will give the intuition for what we're thinking about. Okay, so rather than laying out some, Hamilton, Jacobi-Bellman equations and all of these mathematical expressions right away, I want to just sort of talk you through the type of problem we're thinking about, outline then how uncertainty becomes an important part and how that's incorporated into our analysis. And then I'll lay out a little bit of the specifics of the model and highlight some numerical results. So first, we're going to consider what we in sort of economics and macroeconomics and finance consider a relatively standard optimization setting. So we're going to solve a social planner's problem. So there'll be some, think about this as a global model with the benevolent government trying to maximize lifetime expected utility. Okay, so we have some flow function of utility that will depend on states of the world and actions that we make, policy actions that we make. There'll be a Hamilton-Jacobi-Bellman equation that characterizes this recursive solution. It's dynamic. We're thinking about consequences of our actions today influencing future outcomes, and that's the planner's problem that they're going to solve, and it will give them some value function v of x. That again depends on this discounted flow utility function, which, as I said, depends on states and actions. And so there'll be a vector of state variables in the model, and those will be things like temperature and capital and climate-related states, and they'll evolve with some drift, some volatility, and potentially some jump process. So here x is our state vector, alpha t is our action vector, and then wt and this nt are going to be Brownian and Poisson processes in the model. Okay. Now, in this very standard framework that I'm sort of just putting out there without giving explicit equations, we're going to introduce both jump and diffusion misspecification aversion. So what does that mean? Well, we're going to follow some of the previous economic literature by Hanson and Sargent and Macaroni and co-authors, where we take this very standard maximization of lifetime expected utility and break it into this sort of two-player zero-sum differential game. Now, on the one hand, we still have a player who's going to be engaged in this maximizing social welfare exercise that we have in our standard optimization. But you could think about a second player in the model who's optimizing adverse consequences of uncertainty. And there's a relative entropy penalization saying we're going to consider or limit or bound the types of model discrepancy we consider, but we're going to adjust the optimal sort of socially maximizing policy decisions we make, taking into account the fact that our model could either be ambiguous or misspecified, and we want policy decisions that are robust to these types of adverse consequences. Okay, so uncertainty aversion is going to adjust our standard optimization in the following way. You could think about a standard Hamilton-Jacobi-Bellman equation where you have the derivative of the value function multiplying the drift showing up in our equation. And when we introduce misspecification, particularly in the form of state-dependent drift distortions, we think about that drift, that diffusion process being misspecified and there being some component h, which is going to distort the drift in that process, where it's bounded by a relative entropy term. That's the C sub r 1/2 of h prime h. You could think about this as a type of probability distortion in the Gersanov theorem way, where we're taking this difference in models and mapping it into a drift distortion, where the drift distortion h depends on the magnitude of this parameter CR, the magnitude of volatility on these state variables, as well as the marginal value of changing the states along different dimensions. Now, when we're thinking about misspecification in the form of an altered expected jump outcome, we're taking and adjusting the standard, arrival rate multiplied by the expected change in the value function. And we're altering that by introducing here a probability distortion G, as well as a penalization in terms of relative entropy for how far those distortions could be. Here, that distortion G is showing up in the form of an exponential adjustment to the probability distribution of potential realized outcomes of the state variables from the jumps. Now, all I want to highlight here is that we're taking these standard optimization problems and introducing a minimization component that adjusts the probability of interest for our expected outcomes. And so it's this max-min problem that's linking the decision-making of our social planner in the model to uncertainty outcomes. So rather than thinking about the types of uncertainty quantifications where we're averaging over outcomes ex post, or we're considering different realizations ex post, we're taking this and ex ante incorporating the uncertainty about the model into the decision-making process of our social planner and allowing that to feed through and impact the optimal policy choices made in the model. Explicitly, we're going to consider altered probabilities in our framework along the following dimensions, where we've got misspecification about the damage distribution and the arrival of climate damages. misspecification potentially about technological innovation and its arrival, as well as misspecification related to the climate sensitivity model. And I'll outline what each of these will look like in a minute. From the decision maker's perspective, this CR parameter that we've introduced is a type of preference parameter that governs the aversion to uncertainty, broadly conceived in the model. The constructed worst case probabilities, these H and Gs that I showed you on the previous slide, coming from the two-player game, act as uncertainty adjustments in the social planner's valuation formulas. And importantly, the altered probabilities are not intended to be the beliefs of the planner. We're not endogenously deriving the beliefs of the planner, but rather we're endogenously deriving the sort of concerns about uncertainty. And so these G and H's reflect the magnitude of uncertainty and the concerns that the planner has to help them determine policies while confronting these uncertain possibilities. Okay, so that's the uncertainty framework. And now I want to jump right into the model specifics to highlight how these are going to show up in our framework before I then give some numerical results. So let me start with simplified climate dynamics. Now, the geosciences suggest approximations that simplify model comparisons, right? Rather than taking these large-scale atmospheric ocean general circulation models, which we just simply can't embed into our frameworks, we're going to use something more along the lines of what H. Damon Matthews and co-authors and various others have followed up finding that they've purposely constructed approximations or summaries of climate model outputs. And the one we're particularly interested in is this transient climate response to cumulative emissions, where changes in the temperature anomaly or the change in temperature relative to the pre-industrial level are approximately this TCRE parameter, here we're calling it theta, multiplied by cumulative carbon emissions. Now, this abstracts from transitory weather fluctuations, but what it does for us is it incorporates the fact that emissions today have long-lasting, in our model, permanent impacts on temperature in the future, where the TCRE, this transient climate response, is going to be our climate sensitivity measure. So what does this look like in our framework? Where we're going to use pulse experiments from work by Jose and co-authors and Joffrey and co-authors, which look at carbon emissions impulses and how those impact atmospheric concentrations, and then pulses to atmospheric concentrations and how those impact temperature outcomes. And we're going to combine those different pulse experiments to generate a set of climate sensitivity TCRE parameters, right? So the left plot here, I'm showing you the impact over years of these combined pulse experiments with the red shaded region showing the spread in these possible outcomes. The histogram on the right is essentially a discounted representation of the final outcomes that we show on that left plot. And you can see that there's a pretty large spread in potential outcomes. So for this pulse, you can get anywhere from a 1 to 3 degree temperature response, highlighting that with each of these pulses running through 144 different models presented from Jose and Joffrey in the combination of their analysis, there's a pretty diverse spread in how significant and severe the climate impacts could be. Now, the way that we're going to model that is using a dynamic stochastic climate model where, again, changes in temperature, where YT is our temperature state variable, are proportional to emissions, ET, where the sensitivity to those emissions is theta M, and M represents different potential models from this histogram of possibilities, plus a stochastic component. Now, the stochastic component serves two purposes here. One, it allows us to sort of mask the model uncertainty, make it so that we don't know which theta M, for example, or whether or not this model is misspecified. But also, as has been talked about in the climate science, it helps in terms of improving predictability and strengthening the climate models and representing some of that internal variability, which is important in those frameworks. And so this is gonna be our very simple and straightforward climate dynamic model that involves endogenously. The second part of our model is going to be stochastic damages, where here we're going to use a piecewise log quadratic damage function. So think about N as our damages in the model, right? And that's going to be scaling final output, and it's going to be a function of temperature. And so when you take the log of damages, you end up with either a quadratic component or a modified quadratic component. Now, how does this work? Uncertainty is going to come across in the form of a jump process with L absorbing states. Each state corresponds to some value of lambda 3. starting at y bar. And prior to each jump, the value of lambda 3 has some prior probability pi d, right? So we're going to allow for the fact that there are potentially different damage models that could be on the table. Initially, we don't know which one is the correct one, and there's some jump intensity such that when we reach a range of potential threshold or concerning regions of temperature change, explicitly in the model, this is about 1.5 to 2 degrees, sort of in line with concerns in the Paris Accord and recent IPCC reports of where damages could be severe and irreversible. And then at some point, y tilde within this range, there's going to be a realization of this jump, and the planner goes from not knowing which climate or damage model will be in to knowing that we've reached potentially less or more severe damage outcomes, right? So we start along this first branch of lambda 1 y plus lambda 2 y squared, and then we reach some threshold and jump where we introduce additional curvature through lambda 3. We think this is a nice sort of reduced form representation of potentially severe and unknown future damage outcomes related to climate change. But importantly, the information dynamics here differ from much of what we've seen in the past, as typically there's either a static damage function or uncertainty that is never revealed. And here we're trying to model a very simple form of learning where we don't know the true model outcome at first. And as they become more or less severe in the future, we recognize how severe these potentially could be. Just to give you an idea of what these damages look like, here we have two plots with temperature anomaly on the x-axis and the proportion reduction in economic output on the y-axis. In the first plot, you see that if this jump is realized at 1.5 degrees, the spread in potential damage outcomes is mapped by this red shaded region, can be quite severe, ranging from anywhere to 98 to almost more than 70% of GDP. So you could lose something between 2 to 25% of GDP from the damages as we get to 3 degrees Celsius. That can be quite severe. Now, the dynamic component is that this jump may not be realized until later. And so if that jump happens at 2 degrees, let's say, then there's still a spread in potential damage outcomes, but the magnitude of losses is more along the line of 1 or 2% to maybe 15%. And so this is the uncertainty, both in terms of when we recognize how severe climate damages could be, but also how severe they would potentially be, how adverse those consequences will be in the future. Okay, now let me introduce the economic part of the model here. The planner in this problem has log preferences over damaged consumption, and the output in the model is generated using an AK production technology. So what's going to matter for the planner in terms of producing output is the level of capital that they have, where K here represents the capital stock. And capital is going to evolve in a pretty standard macroeconomic fashion, where changes in capital will depend on some depreciation rate. IK is going to be the investment made by the planner in capital stock. And there's going to be some convex adjustment costs so that you can't simply adjust your capital fully all the way. You have to pay some cost in order to do that. And that means it takes some time to build up the amount of capital that you want. Here we're thinking about capital as being pretty broadly conceived, including things like human capital or intangible capital. Importantly, utility is going to be negatively impacted by economic damages from climate change. So production is going to generate emissions. That's going to increase climate change, and then that's going to influence the magnitude of climate damages. Again, I've stated here that utility is negatively impacted. You could think about rewrapping this in terms of losses on output, which is a pretty standard way to write this down, where we're thinking about losses applying to all parts of output, so production, investment, and it would show up in a very similar way in this framework. Okay, now there's an important lever that can be used in this model in terms of the policy, and that's related to carbon abatement. So we're going to consider the following costly carbon abatement technology. So again, emissions are going to be proportional with some carbon emissions intensity beta, and that's going to be dependent upon the level of mitigation done, and here we're denoting that with iota. Now, the cost of abatement is proportional to output. So again, alpha K is output, and phi 0 iota to the phi 1 are going to be the costs related to the investment in abatement given in a given period. Now, importantly, we want to allow for innovation, and innovation is going to reduce beta T, this carbon intensity of output. And the arrival rate of our innovation is going to be based on some knowledge stock J, where changes in J could have some potential depreciation to the knowledge stock. There's some power function that's determining the returns to scale of investment, where IJ here is R&D investment, as well as, again, some volatility. And again, IJ, which is the R&D investment, increases the knowledge stock, which then increases the technology jump arrival rate, denoted by this I of J. Now, the way that we model the technological innovation in our model is that it's a shift to carbon neutrality, and it's a one-state jump process. So before the jump takes place, beta T is just given by some constant value beta bar. And then post-jump, beta T shifts to 0. So this is a strong and very large technological innovation. We're thinking about sort of breakthrough technology innovations that you could think of in previous energy investments, or things like, investment in nuclear, the atom bomb, or in sort of lunar exploration. These are sort of large breakthrough technology shocks we're thinking about here. And investments in the model are going to satisfy some type of an output constraint, where output is going to be equal to investment in capital, investment in abatement, investment in the knowledge stock, and consumption. Okay, so that lays out the basic components of the model. And so what we want to do now is look at some of the quantitative implications. So we're going to compare and explore the following numerical cases of our model. We're introducing, again, multiple climate and damage models. So we're going to have a theta bar here, which is going to be the average theta based on 144 climate models that I showed you before. And we're going to allow for misspecification across that set. And then we're going to have 20 different damage models. So that so that's a typo there. That should say lambda 3, but that damage parameter, that additional curvature being introduced into the damage function, is going to range of anywhere from 0 to 1/3. And that's what gave us that red shaded spread that I showed you before. We're going to have 20 different models with a prior probability distribution on which of those models could be correct. Again, we've got multiple channels of model uncertainty coming through misspecified jumps, both in terms of the damage function realization and in terms of the technological change. And then we're also going to allow for misspecified climate model dynamics. So whether or not that TCRE representation and that theta parameter, what that value is potentially misspecified. We're also going to consider varying magnitudes of uncertainty aversion. So that CR parameter that I showed you earlier when outlining the model uncertainty framework, here we're going to allow for 3 different values. And we're going to, when CR is infinity, so very large, we're going to call that the aversion neutrality setting. Basically, that just averages over outcomes, and it's basically your standard optimization framework. When we make CR smaller, and we're going to consider 2 cases, 0.05, which we'll consider less aversion, and 0.025, which we'll consider more aversion. These are going to be increasing levels of uncertainty aversion. So as XC gets smaller, the level of uncertainty aversion by the planner gets larger. And the remaining parameters here are set to try and match climate outcomes and the economic literature and data. And again, this is more about quantitative storytelling. So we want to sort of identify and demonstrate where the key channels showing up, recognizing that this is a stylized model that we're going to be building on in the future as well. So let me start out here with our first set of results. This is the distorted climate model distribution. So if you look at these 2 panels, you'll see this red histogram was the same histogram I showed you before, related to different climate model sensitivities, okay? Panel A, what I'm calling less aversion, shows the blue histogram overlapping the red histogram, and that's when we allow sort of a lower level of climate model uncertainty aversion, and how this distribution is shifted. So this is taking that theta distribution and shifting it with this H star to highlight how uncertainty is adjusting endogenously determined in the model. And this is at about 10 years into our model solution simulation. And you can see that there's a relatively modest adjustment from the left tail, meaning sort of low sort of climate change implications, towards the right tail where climate change would be more severe. And as we move to higher aversion, the right panel that we call more aversion, you can see that this distribution shift is increasing, but still fairly modest. And so we're seeing pretty small impacts in terms of the climate sensitivity, but we think that this uncertainty aversion may be showing up in other places. So the second set of results that we'll look at here are distorted damage model distributions. So if you remember, I talked about having 20 different damage models on the table. The red distribution, this red histogram in each of the two panels, shows the baseline. So these are the prior probabilities. It's an equal weighted probability across all of those damage parameters. And then the blue histogram shows the distortions that we get for less or more uncertainty aversion. And again, you see that the distribution here is shifting weight in terms of how the planner wants to make decisions. They're shifting weight from the left tail, sort of the least severe damage setting, to the right tail, where they think that they're going to put potentially more weight on more severe damage outcomes in order to help determine policy choices that are more robust to severe outcomes. And we can see that this is relatively modest again. And as we increase the aversion to uncertainty, we shift more weight from the left tail to the right tail. But again, these are relatively modest adjustments to the distribution. So finally, let me move to the last channel where we're able to identify the impacts of uncertainty through sort of the distributional properties. And here we're looking at the probability of technology and damage jumps. So the left-hand side, we have the technology jumps, and this is the probability that the jump has taken place in the model. And we're letting it run from 0 to 40 years across 3 different cases: the neutrality, less aversion, and more aversion. And the right panel shows the same thing. It's the probability of a jump having taken place, but this is for the damage function. And this is where you can finally see where the uncertainty is most relevant in the model. You can see that as the level of uncertainty aversion increases in the model, there's a significant shift in the sort of distorted probability of this technology jump taking place. And what that means is the planner is putting more and more concern and loading a lot of this uncertainty aversion on the technology jump. The channel that's sort of most relevant for them in terms of uncertainty is, when is this technology jump going to take place and how much that's going to influence the outcomes in the model. And that's what's really showing up in terms of how the planner is considering adjusted probability distributions and what's most relevant for making their policy decisions. You see some spread in terms of the damage jump, but again, the most significant effects are showing up in their concerns for technology aversion or technology change. So now that we know sort of where this uncertainty aversion is most relevant for the planner, let me highlight how that influences the policy choices made by the planner. This first set of plots is showing you R&D investment optimally determined in the model, and we're simulating out between 1 and 25 years across, again, on the left-hand plot, 3 different levels of uncertainty aversion. So the neutral case, the less and more aversion. And then the right-hand side, we're going to vary which channels of uncertainty that are playing a role in the model. So the blue line shows just climate aversion, the green line shows just damage aversion, and the red line shows just technology aversion as being relevant in the planner's decision-making. Here we highlight 2 key results. First, as we introduce more uncertainty aversion, the level of R&D investment put in by the planner to help increase the likelihood of the technology shock is significant. And so we're seeing almost a doubling, and this is R&D as a percent of GDP, a doubling and even more of the amount of investment in R&D investment made by the planner. So the R&D investment is very sensitive to the level of uncertainty aversion. And in the right panel, where we look at the channel comparison, we see that damage and climate uncertainty play a very small role in influencing the R&D investment choice, but clearly the technology aversion channel is augmenting the choice of a R&D investment pretty significantly. If we were to look instead at the emissions pathways, okay, again, I'm showing in the left panel different values of uncertainty aversion, and on the right panel, different channels of uncertainty and which ones influence the choice of emissions. We actually find something very interesting that's pretty starkly different from some of the frameworks we've seen before. As we increase the level of uncertainty aversion, we see that clearly the level of emissions decreases. And if you think about the current level of emissions, that's about 10 gigatons of carbon. So up front, there's a pretty significant reduction in terms of the level of emissions used in the economy. And as the uncertainty aversion increases, the level of emissions decreases as well. However, two things to note is that in terms of relative magnitude, the sensitivity of emissions is far less than we saw, right? We saw a doubling of R&D investment and a more modest reduction in emissions here, as well as the pathway of emissions could still be increasing. So rather than sort of focusing on emissions and paying significant costs to reduce emissions through abatement, what we're seeing is that the planner puts a lot of weight in terms of R&D investment to produce the carbon neutral technology that then will allow them to bring down emissions. Again, note that technology aversion is playing an important role, the most significant role in terms of what's mattering for uncertainty. Now, I mentioned this earlier, and I'll just sort of briefly highlight this, that we can look at social valuations as a metric for measuring the impact of uncertainty. This is where sort of the finance type of component of the paper shows up, where we can depict social valuations as asset prices, where we have social cash flows related to impulse responses, either for R&D or for future climate states. And the cash flow is discounted stochastically, altered by these uncertainty adjustments as changes in probability distributions. So let me just show you two ways that this helps us highlight the outcomes in our model. Here I'm showing you the social value of R&D in log scales. And what you can see as you compare in the left panel, the aversion comparison is that, again, increasing uncertainty aversion leads to a higher social value of R&D, which is driving this increased R&D investment in the model. And as you look at the channel comparison across different channels of uncertainty, again, it highlights the technology aversion is playing the largest role in increasing the social value of R&D in terms of the effects of uncertainty. You see a similar story if you look at the social cost of carbon. Again, uncertainty increases that social cost of carbon, and it does mostly through the technology aversion channel that we've been talking about. Now, I'm about out of time, so that we'll have lots of time for Q&A. I'll just highlight that, the quantitative results in this framework are sort of special to a number of pieces that are in the framework. We're thinking about a single big event R&D outcome. We also think that, the cost of abatement, which we're borrowing and following the previous literature on this, is arguably too low. And as well as the fact that you could think about a more extended preference structure where we think about the elasticity of intertemporal substitution being different from the implicit value of one here. Each of these could play important roles in thinking about how severe these outcomes could be. There's also additional policy channels to consider, whether it's property rights and subsidies or returns to R&D investment and uncertainty about that. And we have specific plans for exploring each of these, but I haven't talked about those today at all. There's also lots of other alternative model settings that we could consider, things that we're exploring now, whether it's clean and dirty capital as the setup, endogenous tipping points where we think about scientifically motivated bifurcations, spatial heterogeneity, and the need to solve these frameworks in alternative numerical settings, such as using deep neural net computations. All of these are sort of on the board for things that we're thinking about that aren't here, but are really interesting channels that go and add to this level of uncertainty analysis that we think is quite interesting. But let me just wrap up here so we'll have time for Q&A. To conclude, we've highlighted that model uncertainty is prevalent and important along multiple dimensions, including carbon climate dynamics, economic damages from climate change, as well as green technological innovations. We've put down a framework which we think is tractable to using decision theory uncertainty to guide uncertainty quantification related to the design of climate policy in such settings, where we've allowed in this setting jump and diffusion model misspecification, but we're also exploring and have highlighted in the paper roles such as alternative uncertainties related to smooth ambiguity. And what we find in our analysis is important implication for policy choices that are impacted by endogenous equilibrium responses to uncertainty. where the planner in our model relies heavily on R&D and not on dynamic emissions reductions. Technological uncertainty dominates climate and damage uncertainty in terms of what the planner cares about most when making their optimal policy choices. And R&D is substantially more sensitive to uncertainty than emissions, highlighting that when multiple policy levers are on the table, that there are important implications in terms of which policy lever the planner uses, how they use those dynamically, and which channels of uncertainty influences those different policy choices the most. So I will end there and look forward to your questions and further discussion.